Hi, my name is Ted Pavlic, and I am an engineer at Arizona State University, and I work with, among other things, ants. This particular project is a collaboration with some astrobiologists and behavioral ecologists where we focus on some interesting behaviors of a crevice-dwelling ant from the genus Temnothorax. And this particular ant has a conspicuous quorum sensing behavior. It's a great model for quorum sensing in animal systems where scouts, when they are looking at new candidate nests, when they detect that there's a low number of ants at that nest, they will return to their home nest and recruit new scouts using this behavior you see on the left, known as tandem running. So it's a very conspicuous 2-by-2 behavior where they follow each other all the way back. Whereas on the right-hand side, you see what happens when they detect that there's a high number of ants in the candidate nest. They come back to the home nest and they grab a nestmate and throw them onto their backs and run with them. So they transport that. So we have these two behaviors that we can readily observe in the lab: tandem running and transporting. And when we look at what happens in the candidate nest before they make the decision, then we see that there is a critical encounter rate with ants in the candidate nest, under which all decisions are tandem runs, over which all decisions are transports. So it seems like they're using this critical encounter rate as a cue. Moreover, if you look at how long they stay in the candidate nest before exiting and making a decision, you get a peak latency around where that critical encounter rate is. It's not exactly there, but it is around there, and then it tapers off to the left and right of that. Now, these particular latency and accuracy curves seem to match what you get in cognitive psychology when you put humans in difficult classification tasks. And so the psychologists have taken phenomenological models that assume that there is a random walking around the brain of the individual, and that random walk, as it hits different barriers, then gives you the latency and accuracy curves that you get out like this. But what we notice is that ants are doing their own random walk around their own cavity. So they may not need this internal cognitive process. And so if you simulate, for example, a bunch of billiard balls that are bouncing around a cavity, and you follow one of them and see how long it takes for it to re-find the entrance that it came in on, then what you find is the time that it spends in the cavity as a function of encounter rate with other billiard balls has the same peaky shape that looks just like what we get with the ants. So it might mean that these latency curves are really just an epiphenomenon of being in a cavity. So in that case, what would a decision-making mechanism look like for ants that aren't deliberating, but instead are just bumping into other ants? And so the thought is maybe they're mobile excitable elements, mobile neurons that have their own action potentials, that when an ant bumps into another ant, it becomes activated. That activation decays, but during the decay, if it bumps into an exit, it does a transport. If it gets all the way back to its quiescent state and then bumps into an exit, it does a tandem run. And if you simulate a bunch of those ants moving around a cavity together, then what you get is that with few numbers of ants in a cavity, then you find that these ants, where the quiescent state is the red state here, bounce around, they almost never hit each other, and by the time they find the exit, they're almost always in the red quiescent state, and so they do a tandem run. In intermediate densities, ants can get in, but then they kind of get stuck, and they'll stay in here for long amounts of time. Meanwhile, all the ants in the cavity will either be, half of them are going to be in the quiescent state, half of them are going to be active state, and those that get out will either do a tandem run or a transport with a 50-50 probability. In the high density state, all of them go into the transport state, the active state, and any new ones almost immediately bounce out in the transport state. And so we can end up, doing the density classification here. So here, this is a bunch of different simulations at a bunch of different encounter rates. And what we find is something that looks exactly like the ants, with a very sharp discrimination curve, a great, very sharp classification boundary. And it turns out if we change the time constant of those mobile neurons, we can tune exactly where that classification boundary is. So the takeaway point that I'm trying to say here is that if you have mobile excitable neurons inspired by ants, they don't have synapses that have weights that you can tune, but they have cavities. And those cavities, the physical spaces, play the role of those synaptic weights. And so ants may themselves become bio-inspired models for how we can build these types of mobile excitable networks in these physically embodied intelligence systems of the future. That's all I've got for you today. I'm looking forward to other conversations. Feel free to reach out. Thanks.